I'm going to talk about program fairness and try to lend a formal methods perspective to the problem. Basically, what I'll try to show you is how fairness can be encoded as a program property, and then show you how techniques from program analysis and verification can be used to generate proofs of fairness. So this is joint work with Samuel Drews, who's a PhD student at the University of Wisconsin, and his advisor is Ausen Loris. So as we all know, data is everywhere and manifests in various forms. For instance, to name a few data sources, there are more than 5 billion people calling, texting, tweeting, and browsing websites on their mobile phones. Facebook has more than 900 million users generating social interaction data. And there are approximately 340 million tweets that are sent per day. So consequently, developers increasingly need to reason about data as well as code. So data analysis is a big part of today's software. We find that developers increasingly need to reason about data as well as code. They're increasingly employing machine learning models in their software. And we also find that they need to deal with data that is fairly incomplete, noisy, and approximate. So given this state of the world, what are the new programming language challenges? We think there are two main challenges. The first is that of data acquisition and manipulation. With lots of data in the world occurring in zillions of formats, converting to one's favorite format and manipulating the data is a very time-consuming, laborious, and error-prone process. And the main problem here from a programming language's perspective is the large mismatch that occurs between data in the world and programming languages. There are also poor facilities in programming languages to implement these kinds of data transformations. The second challenge is how to reason over data. For this, programs need to naturally deal with machine learning, statistical, and approximate computation. Unfortunately, at the moment, abstractions for these kinds of computations are virtually non-existent. And in this setting, what does correctness even mean for machine learning or decision-making programs? So in this talk, I'll focus on one kind of correctness for a particular property, which is fairness, and try to answer this question. Since we're in the Turing Institute, I thought as an aside, I thought I would talk about Turing in this slide. So the standard references for work on program proofs attribute the early statement of direction to John McCarthy and practical methods to Peter Knorr and Robert Floyd, and the provision of more formal systems to Tony Hoare and Edsger Dijkstra. Here's a paper from Alan Turing, written in 1949, where he asked the question of how to check a large routine in the sense of making sure that it is correct. And it's quite remarkable. He shows that for a program with two nested loops, that one can actually automatically generate a proof of correctness of the program. And the proof method here is very similar to that of Floyd. That said, let's look at how decision-making programs today, or rather machine learning programs based on machine learning, can go wrong. So a recent Bloomberg report revealed that Amazon's same-day delivery system offered to Prime users around major cities seemed to routinely, if unintentionally, exclude black neighborhoods. Here's another example where there's a data-driven program that is used to predict future criminals, and it's biased against blacks. And there are several other examples and reports on which voice concerns about automatically generated programs from data. So what we're interested in is how do we prove that a program doesn't discriminate? And this question is interesting to researchers in various areas too. For instance, for theoreticians, the question is how does one formalize the notion of fairness? And for machine learning researchers, the question is how does one learn fair models which are provably fair and correct by construction? And security and privacy researchers like to ask questions about bias in black box algorithms. And from a legal point of view, how does one regulate algorithmic decision making? And needless to say, this is a very important problem, and it's important to have a better understanding of how fairness and bias in decision-making programs, especially with GDPR looming over us in the EU. There's also this White House report that talks about powerful algorithms, that is, algorithms generated from data, and which raise the potential of encoding discrimination in automated decisions. And more recently, there's a report which talks about taking extra care to ensure the efficacy and fairness of AI-based systems, particularly ones used by federal agencies. Interestingly, they say that the validity or correctness of the systems needs to be based on verification and validation. So in this talk and in our work, we asked the following questions. How does one encode fairness as a program property? And given this notion of fairness, which is a specification, how does one validate programs, which are decision-making programs, and generate automatic proofs of fairness or unfairness? So fairness and justice have been very ripe topics for philosophical debate, and of course there has been no established rigorous definition of fairness. However, the rise of automated decision-making has prompted the introduction of a number of formal definitions of fairness. And over here, I look at one notion of fairness. So here we have a decision-making program D, which gives an output H and consumes an input V. And the input V has a number of attributes. And in particular, let's focus on this attribute V sub S, which is what I call a sensitive attribute. So when V sub S equals true, it encodes 10% of the domain of the population, and V sub S equals false implies the rest of the population. So given this distribution over the inputs, this condition over here encodes the fairness property. So what this says is that the output of the decision-making program conditioned on the sensitive attribute being true is very similar to the output of the program conditioned on the sensitive attribute being false. So essentially what this is saying is that roughly these conditional probabilities are the same. So for example, if the decision-making program was a program trying to decide whether somebody needs to be hired or not, and let's say the sensitive attribute encodes the property which is whether a person belongs to a minority group or not, what we'd like to check is that the probability of hiring a person conditioned on them being a qualified minority applicant is very close to the probability of hiring the person conditioned on them being a non-minority applicant. And here's an example of such a program. So this decision-making program takes an applicant's record and decides whether to hire them or not. So over here, the program takes 3 inputs: the college rank, the years of experience of the person, and the ethnicity. And if the person is hired if they come from a high-ranking college, or if they have sufficient experience, despite the fact that they might come from a low-ranking college. And the fairness property is what we saw in the earlier slide for this example. So what we'd like to ensure is that the probability of hiring the person conditioned on the ethnicity doesn't affect the hiring decision. So it's important to note that for this program, the program does not make use of the ethnicity explicitly. And the inputs to this program come from the space M, and it's important to understand what this space even means. So we call this space the population model. So what happens for this program is that you get inputs from a population model which are fed to the decision-making program, and the program basically decides whether or not to hire the person in question. Intuitively, the population model provides a probabilistic picture of the population from which the inputs to the decision program are drawn. So given this setup, we have a program, a precondition encoded by the population model, and the postcondition which encodes the fairness property. And this is very similar to a Hoare triple, and the question is, given this Hoare triple, is the Hoare triple valid or not? So that's the question we're trying to ask. So as I mentioned, the population model defines a joint probability distribution on the attributes of a member of a population. So in this case, the population model is defined over 3 variables: the rank of the college a person attended, which is given by the variable called rank; the years of work of experience they have, which is given by the variable yexp; and their ethnicity. So note that the college rank is influenced by the ethnicity. And as you can see, we have these three variables, and they are drawn from Gaussian distributions. So this is the input to the decision-making program, and the question again with respect to the correctness is basically the composition of the population model with the decision-making program, whether that satisfies or violates the post condition. So let's focus on the post condition over here, and using conditional probability, we can rewrite the post condition in this manner. And what I'm going to do for the next few slides is to focus on the probability that an applicant is hired and the applicant comes from a minority community. So the question we're going to ask is, with respect to the hiring program, what does it mean for the program to satisfy that condition hire and min? So let pi denote the set of all possible execution paths in this program, DEC, which takes a population model as input. So we have a population model. This is the process of drawing a sample from the population model, and this encodes the path taken by the decision-making program for that drawn sample. And let P of pi be the probability that a particular path is executed. So what we're interested in is the subset of paths in this universal set of paths which satisfy this condition higher and min, and that's denoted by HM. And that's given by this expression over here, which says that the probability of higher and min is the sum of over all probabilities of paths which are in this set HM. And more generally speaking, we'd like to look at not mass functions, but density functions, given that there are an infinite number of paths. So that summation over there can be written in the form of this integral over the set of all paths which satisfy higher and min. So as far as the program is concerned, what does this expression really mean? So again, we have the population model and the decision-making program. And the question we'd like to ask is, with respect to the composition of these two programs or models, what does this integral mean? So let's focus on the population model, where we're drawing samples for these three variables, ethnicity, call rank, and yx. And the thing to note is that each path in the program is uniquely represented by three real values for this program. So the idea here is, it's quite a simple one, which basically says that let's represent each path in the program as a region in R cubed. And let's call this region phi. And given the fact that we are looking upon these paths as regions in R cubed, this expression here translates to integrating over the region phi. And given that these three variables are independent, it's basically the product of these three the density functions. So essentially what this translates to is that we are interested in computing this weighted volume of the region phi, where the weights are defined by the density functions. When there are no probabilities, this expression here is just the volume of the region phi. So what we'd like to do is to ask the question as to how given the population model and the decision-making program, how does one compute these volumes automatically? So here's the volume for the example shown pictorially. And we know that each of the axes here, the values are drawn from Gaussian distributions. The question is, how does one compute the volume? So before we go to the question of how to compute the volume, how does one define formally the region phi? For this, we basically employ a well-known technique in program analysis called symbolic execution. So what we're going to do is to define phi for the population model and define phi for the decision-making program as well. So if we were to symbolically execute this program, this is the phi that we get for the population model. And why is that the case? So if you look at this condition over here, if ethnicity is greater than 10, then the rank is basically incremented by 5, and that's encoded by this implication over here. So ethnicity greater than 10 means call rank subscript 1 equals call rank plus 5, and this is just a standard way to encode updates to these variables. So essentially what's happening is that we have an internal representation of this where the program is assumed to be in static single assignment form. And likewise, if ethnicity is less than or equal to 10, there is no update to column rank, and therefore it remains the same. So the new value of call rank is the same as the old value of call rank. And likewise, for the decision-making program, here is the value, the predicate that encodes the decision-making program for each path. And the variables with superscripts are nothing but the new values, and in particular, the inputs to the decision-making program. So given that we have these two encodings of phi, what we'd like to do is to say that the value, the phi for the composition is nothing but the conjunction of phi pop and phi dec, suitably connected with the input-output variables, between the connections between the input and output variables. So essentially what we do is we conjoin these two predicates and then add equalities between the returns of the population model and the inputs of the decision-making program.
How do you define phi if the program has a loop?
How do you find phi if you have a loop? Then we would need invariants and so on. So in this work, yeah, we just looked at simple programs without loops. So as I mentioned, we perform a conjunction of phi pop and phi dec, and since we're interested in the property, which is that a qualified applicant is hired and comes from a minority group, we have the conjunction of those two variables. And then we also, in this formula, existentially quantify away all non-probabilistic variables or deterministic variables. And the reason, and what this means is that if you want to ask the question, what is so what this means is that in order to compute the probability that a minority applicant gets hired, formally what we're asking is, what is the probability that the following formula is satisfied? So essentially, for this formula, if you look at the set of all models or the set of all probabilistic samplings, that leads to the case where a minority applicant is generated and is hired. So as far as our approach is concerned, we want to take the population model in conjunction with the decision-making program, represent all executions as a satisfiability modulo theory formula, phi. And what we'd like to do is to, again, using an SMT solver, possibly compute the weighted volume of phi. Unfortunately, computing this is intractable. It's a sharp-P hard problem. And the question is, how do we do this effectively? So the problem here is that we have a region of integration that is specified by an arbitrary SMT formula over an arithmetic theory. And the question is, how do we compute a numerical value for this integral? And for this, basically, is the next part of the talk, which is about how to generate automatic proofs of fairness. So let's go back to this picture again, where we have this weighted volume computation, and we want to kind of automatically figure out what the volume of this object is with respect to the densities. And the simple observation is that if these volumes were rectangles, then the integration is easy. To see this, let's take an object which is a rectangle where in 2 dimensions, and let's assume that the y-axis is sampled from a Gaussian distribution, and the x-axis is also sampled from a Gaussian distribution. Then we know that by looking at these two intervals, we can compute the integrals. It's just a matter of integrating this Gaussian in this range and this Gaussian in this range and taking the product. But what about, for example, this triangle over here? So the simple idea that we use is that we could possibly decompose this triangle into a set of rectangles and then use the intuition for the rectangle for each of the sub-rectangles in this triangle. But unfortunately, for this figure, there are an infinitely number of rectangles, and the question is, how do we do this effectively with some provable guarantees? So the general idea here is to use the notion of what we call as hyperrectangular decomposition. So essentially what we want to do is, given a formula phi, we'd like to consider all hyperrectangles or rectangles inside the volume enclosed by the formula phi. And then what we'd like to do is to iteratively sample rectangles from the phi and compute their volumes and then add them up together. So that's the rough plan. So let H be the set of all hyperrectangles in phi. And what we want to do is to compute this formula box sub phi such that there is a one-to-one correspondence between H, the set of all hyperrectangles, and models or satisfying assignments of phi. So this means that if we could construct such a formula, then sampling models from phi would basically give us a way to compute the volumes of subrectangles in any arbitrary volume. So specifically, given our formula phi, we construct this formula box phi, where each model is a hyperrectangle. So over here, we consider phi and look at all the variables in phi, and introduce two new variables for every variable x, L sub x and U sub x, where L sub x is a lower bound on x and U sub x is an upper bound on x. And also add this additional constraint, which basically says that the lower bound is less than or equal to the upper bound. And one can easily show that this formula here is always an under approximation of the formula phi. And every model of box sub phi is indeed a model of phi. So given that we have a way to think about hyperrectangles in any arbitrary formula phi, how do we sample disjoint hyperrectangles from this volume? So essentially what we do is to define an iterative process, which I'm going to describe right now, where we first assume that we first set the volume of phi to be equal to 0, and given a representation of box sub phi using an SMT solver, we get a model M, and let HM denote the hyperrectangle induced by this model, and we know how to compute this volume thanks to the rectangle trick. So we compute the volume of the rectangle induced by the model and augment it to the volume computation. And then what we do is we block all rectangles which overlap with this induced rectangle and repeat this process. And this blocking constraint is easily encodable as an SMT formula. So therefore, we have a procedure which uses an SMT solver as a black box that samples hyperrectangles and computes a volume. And what we can show is that this procedure iteratively always maintains and computes a lower bound on the actual volume phi. So for this example over here, what that procedure can potentially give you is a decomposition which consists of 4 hyperrectangles. So this is one, this is the next, this is the next, and this is the next. And this is a lower bound on the actual volume. So the procedure over there basically is a sound procedure which gives you a lower bound on the volume of phi. So the question is, what are the challenges with actually getting this to work in a practical way? What could go wrong? And there are, of course, challenges with sampling. So one challenge is that you could sample a rectangle which has 0 volume, and that basically results in the algorithm making no progress towards computing a tight lower bound on the volume of the region. And if we assume that this triangle has increasing probability in this direction, then this is the area of high probability. It is quite possible that the algorithm keeps sampling hyperrectangles in low probability regions, which also means that you don't get enough support for your volume computation. So the ideal solution to this process is to further constrain the sampling with the following objective. So what we'd like to do is, of course, we'd like to sample models from box sub phi with this constraint which says that we won't only compute sample maximum volumes. So unfortunately, doing this is a hard problem because we don't have good SMT representations for the densities. So the idea here is to approximate densities with step functions. So given, let's say, this Gaussian, what we'd like to do is to approximate this with the step function or a histogram. And given this representation for the density function, which is approximate, we can encode the density function as a linear formula, and then satisfying that objective in a heuristic manner becomes possible. And there are various ways in which we can approximate this function with step functions. And this has various trade-offs. So for example, more accurate representation of approximation of the density leads to fast convergence, of course, but slow sampling, whereas really approximate gross approximations of the density leads to fast sampling but slow convergence. So that's a trade-off that we need to handle from an engineering standpoint. So the idea is basically whenever we sample a hyperrectangle or a model from box sub phi, we sample it keeping in mind that we've approximated the density with a step function, and we encode the integrals as linear arithmetic formulas. So what are the properties of the algorithm? So we can show that the algorithm always maintains a lower bound on the volume, and we can also show that in the limit it converges to the actual volume. And the algorithm actually is designed for real closed fields. So essentially, it subsumes linear real arithmetic, so Boolean combinations of polynomial inequalities. And to compute upper bounds, we just use the simple trick of negating the formula. So given this equation over here, volume of phi is nothing but 1 minus volume of its negation. We can easily compute the upper bound on the volume of phi by applying the algorithm to the negation of phi, which gives you a lower bound, and subtracting 1 from that. So given this algorithm for computing weighted volumes, how do we get proofs of fairness? So if you go back to the post condition for the example, so here we'd like to compute the probability of higher, given that the applicant is from a minority group, versus the probability of higher, given that the applicant is from the rest of the population. What we do is we use the algorithm to compute a lower bound in the numerator, and use the algorithm again to compute an upper bound of the denominator. And if this lower bound divided by the upper bound is greater than 1 minus epsilon, we have a proof of fairness. And for the proof of unfairness, we do something similar. So we use the algorithm to compute an upper bound of the numerator, and again use the algorithm to compute a lower bound on the denominator. And if this violates the inequality, then we have a proof of unfairness. Okay. So we have a toy implementation of the algorithm, and essentially what we wanted to check was whether our tool could verify fairness properties of toy machine learning programs. We haven't still graduated to real-world machine learning programs. So what we did was to take a popular data set called the adult income data set, and the decision-making program that we considered was a salary decision program, and we wanted to check if it was fair with respect to qualified female employees. So the first column in this table over here are 11 decision-making programs trained on this data set. So we used decision trees, SVMs, neural networks. And for our population models, we considered 3 population models. One was a model which assumed that all variables were independent. So it was a trivial model where there is no chance of unfairness. So one would expect, so this was our baseline model, and one would expect our tool to prove the correctness of all decision-making programs with respect to this population model. The other two were slightly sophisticated. One was based on clustering, and the other one was a Bayesian network, which introduced correlations between the variables, and therefore it was interesting to see whether the decision-making program that we designed could be unfair. So as you can see, all the check marks basically are the cases where we were able to prove fairness, and all the crosses are all the cases where we proved unfairness. For the cases where the tool timed out, so we ran the tool for 900 seconds, and if it did not produce an answer, we report the lower and upper bounds on the numerator and denominator over here. The last two rows are quite interesting, because if you look at DT1 or DT16, which is this one, for the cluster population model and for the Bayes-net population model, we obtained a proof of unfairness. And what we did was to modify the decision-making program in a fairly trivial way to implement rudimentary forms of affirmative action. So what we did was that for the decision tree, there was a 15% chance to flip a decision which gave a low salary for a female, and for the SVM, the linear separator was also moved appropriately. So given this rudimentary form of affirmative action for the modified decision-making programs, our tool was able to prove that the modified versions were indeed fair. Okay, so to summarize, I've shown you an approach which is the starting point for obtaining automatic proofs of fairness or unfairness for decision-making programs. There are lots of interesting future directions. So as I mentioned earlier, we need to do some more work to get our techniques to scale to real-world machine learning applications. It's also interesting both from a transparency as well as a machine learning point of view to explain unfairness. So given a proof of unfairness, can we actually root cause the reason for unfairness? And then, of course, how does one repair unfair programs, and possibly also design programs that are fair by construction? So further details are available in this paper over here. Thank you.